Welcome everybody to this third session. I am recording this offline now because there were some technical difficulties that are ultimately due to me screwing up the recording. So that's why I record this content session really quickly for you guys offline so that you have the content available as soon as possible. So let us put our toes into probability land again. First of all, you do not have to worry. This is going to be a little overwhelming for some, not as intuitive for others, but be reminded you do not have to be able to explain Bayes' theorem. That is the scary thing we will try to approach now. Having heard it once or twice and being able to read up on it is absolutely sufficient. I will try to signpost the important conceptual take-homes, and if you grasp those, you are in great shape. Now, I have recently moved to Norway, and I have lived in a few places by now, but as many of you know, when you move to a new country, you have to get used to the weather. And that's a big deal in Norway. One of the larger existential questions that Norwegians have is whether it's going to rain or not on a given day. And this can obviously have very practical implications about your dress code or whether you take an umbrella or not. Now, imagine one morning I wake up in my dark bedroom and I start wondering whether to take an umbrella with me before I leave the house or not, whether it's going to rain or not. I have not yet been outside, so I don't really know what the weather looks like. Let's assume whether it rains or not might be a coin toss based on my experience, or slightly skewed distribution because I've encountered more sunny days than rainy days so far. Well, we'll get back to that in a second. As I gather my things, however, I happen to stand in front of a large window and I notice some scary looking dark clouds on the horizon. And based on this new information, I might reconsider my beliefs about whether it'll rain or not. Right? So I will reconsider this initial belief I had. But one step back, what exactly do we mean when we talk about probability? You are probably all like, this is super trivial, but it's not. The concept is not trivial, and when talking about inferential frameworks like we do here, it actually matters a lot, because null hypothesis significance testing and Bayesian inference operate on different notions of probability, as Joseph already mentioned earlier. Intuitively speaking, the probability of an event, say whether it rains or not, is a number that represents the uncertainty associated with the event's occurrence. In everyday life, people often use percentages to denote probabilities. For example, the probability that a fair coin will land heads is 50%. For more convenient representations, mathematicians use a decimal, 0.5, to refer to the same probability. Now, under this convention, an impossible event would have a probability of 0, and an event that is certain to occur will have a probability of 1. An event whose occurrence has some degree of uncertainty will be assigned a real number between 0 and 1. The closer an event's probability is to 1, the more likely it is that the event will occur, and vice versa. That seems all super boring for you, of course, but bear with me, okay? The conventional notation for expressing probability is probability in brackets event. So here, P of rain is the probability of rain. Now let's assign some numbers to these probabilities. Okay, let's say the probability of rain is 0.3. Right? My expectation here, and I realize there's still a mistake on the slide. It should be on the top right-hand side. It should be 0.7. Okay, so 0.3, probability of rain, probability of not raining should be 0.7. Now my expectation for rain are equivalent to my expectation to draw a purple ball from a bag of 100 balls, including 30 of them being purple. Okay, so how do we arrive at this probability? Well, maybe living where you live, maybe living in Oslo, 30% of the days I encountered it actually rained, while on 70% of the days it didn't. So knowing nothing else, just the frequency of rainy versus sunny days, my best guess is 0.3. Note that there's still plenty of uncertainty, right? It is not super unlikely to pull a purple ball out of the bag, but it's slightly less likely than pulling an orange purple out of the bag, meaning, it's going to be sunny. It actually has consequences, right? Our estimation of probability. If I take the umbrella and it doesn't rain, well, the umbrella is just a nuisance, and me personally, I lose my umbrellas usually. If it does not rain and you don't take an umbrella, well, you will be soaking wet. So, consequences here. So what do? We have to realize, though, that this example so far is a little bit unrealistic. We usually have several sources of information we take into account when assessing probabilities. For example, we gather more evidence. So in my scenario here, I gather more evidence. I look outside of the window and I see some scary looking dark clouds on the horizon. Now, you can ask the following question. What is the probability of these dark clouds on the horizon given that it will rain? So you aren't simply interested in the general probability of seeing these dark clouds. You want to know the probability of those clouds relative to whether it rains or not. In probability theory, such probabilities are called conditional probabilities, and the notation used for them looks something like this on the bottom here. Conditional probabilities express the probability that event 1 will occur when you assume or know that event 2 has already occurred. Right? So what we have here is the probability of these dark clouds on the horizon given that it will rain, and I assign this conditional probability 0.8. So I believe that the probability of seeing these clouds when it actually will rain are 80%. And I believe that seeing these clouds, the probability of seeing these clouds when it won't rain might be 20%. Okay? So big question, do I change my guess? Do I change the probability that I assign to the event of rain given that I see these dark clouds on the horizon, given the evidence? Does my estimated probability of rain change? And if so, how? Okay. So the conditional probability that a random day with these dark clouds on the sky is going to be a rainy day, in this case, is 63%. So 24 out of 38. Before we understand how we arrived at that number, we have to understand what happened here. What happened is I updated my initial belief of 30% after having seen the dark clouds. Right? Note that this actually makes my guess a little bit more uncertain. Before, I was kind of certain that sunny Norway won't rain on my parade. It's more likely to rain. After seeing the dark clouds, I'm kind of uncertain. I'm actually slightly more certain that it will rain. However, it could go either way, really. So there are two important concepts so far. One is uncertainty, that is how certain we are in a particular event. And the other is belief updating, referring to the fact that we change our beliefs in the probability of events based on new observations. Okay. Now, how do we actually arrive at this number 63 here? You probably guessed it, Bayes' theorem. In mathematics, true statements are called theorems. These are statements whose truth you can prove using logic. The Bayes' theorem is named after the British statistician and philosopher Thomas Bayes, who first discovered it. So that's where the name comes from. Now, the general situation where Bayes' theorem is relevant and useful, and you might already see where this is all going, is when you have some hypothesis. In our case, that it's going to rain, and you see some evidence, dark clouds on the horizon, and you want to know the probability that the hypothesis holds given that the evidence is true. And we can write this as a conditional probability statement, the probability of the hypothesis H given the evidence E. So we are restricting our view on the possibilities where the evidence holds. Now, how do we get there? The first relevant number is the probability that the hypothesis holds before considering the new evidence. In our example, there was 30 out of 100, which came from, considering the ratio of rainy days and sunny days in Norway. Right, so we literally count the purple balls, 30 out of 100, that's 0.3. Okay, this number is known as the prior, our belief in the probability of rain before we have received any new evidence. After that, we encountered evidence. We needed to consider the proportion of rainy days that fit this evidence, the dark clouds on the horizon. The probability of seeing dark clouds, given that the hypothesis, it's going to rain, is true. So when you see this vertical greenish bar here in the background, it means we're talking about a proportion of a limited part of the total space of possibilities. In this case, limit to the left side where the hypothesis holds, right, where the prior holds. In the context of Bayes' theorem, this value here, the probability of evidence given the hypothesis, is called the likelihood. Similarly, we need to know how much of the other side of our space includes the evidence, the probability of seeing the evidence given that our hypothesis is not true. Okay, so we should have all we need now. Attention, it becomes slightly mathy now, but only a little bit, and I will offer you a more spatial way of thinking about the upcoming formulas. So bear with me. Remember what we just said. The probability that our hypothesis is true, that it's going to rain given the dark clouds, is 24 out of 38. So all of those icons that have a green background are related to each other. Right? The total number of rainy days fitting the evidence, that's all the purple balls with the green background, divided by the total number of days fitting the evidence, both rainy and sunny days. Right? That's 24 divided by 24 plus 14. Now, where do these numbers come from? Where does the 24 in the numerator come from? For short, it's the product of the prior and the likelihood. So it's the total number of days, 100, times the prior probability of being a rainy day, that's 0.3, so we end up with 30 here, times the probability that one of those fits the evidence, which was 0.8. So 0.3 times 0.8. So the prior times the likelihood goes into the numerator. Okay. That same number shows up again in the denominator, so 24 here, but we need to add the proportion of days which are not rainy days multiplied by the proportion of those days which fit the evidence, adding up to 38. Right? If we step away from the arbitrary chosen numbers of days, we are left with the more abstract representation purely in terms of probabilities on the right-hand side. Right? And this, my friends, this is Bayes' theorem. And if you're confused, you're supposed to. If you're not, you're a monster. This part of the presentation is a really good part of this workshop that should be revised and reviewed a couple of times. So we can simplify the denominator usually on the right by writing the probability of evidence. So the total probability of seeing the evidence is in the denominator, which makes the formula much more wieldable. Right? Piling on one final bit of jargon, and that is something that Joseph already mentioned. The final answer, the probability of the hypothesis given the evidence, that is what we call the posterior. Our belief about the probability of the hypothesis after seeing the evidence. So, this is Bayes' theory. Now you've heard about it, now you have a rough idea what's going on. And to remind yourself how it works, I think the spatial representation of this square of 100 balls, circles, whatever, is a very helpful way to conceptualize the relationship between individual components of this theory. So for example, I could improve further on my beliefs, right? I could improve my guess even more by checking the forecast on a weather app. So the posterior of the first iteration of belief updating, after seeing the cloud, will function as the prior for the upcoming update. And as Dennis Lindley famously said, today's posterior is tomorrow's prior. So if you repeat gathering evidence over and over and over again, you will update your beliefs over and over and over again. This is conceptually what happens when we use Bayesian methods in the context of, for example, a linear model. We have a prior about a certain regression coefficient or any other parameter of the model. Say, how much does attitude affect F0 in speakers? We measure one sentence, we update our belief about that quantity. We measure again, we update, we measure again, and so forth and so forth. Each data point means another update of our beliefs. And we will obviously dive into that a little later. Right. Now back to the rain example. Let's assume I have arrived at believing in an 80% probability that it will rain. Big question is going to be, do I bring my umbrella, right? This last question is an important one because based on an uncertain event and a few observations, I might have to make a decision. I might have to act. Right? So what would you do? Would you bring one? Now this question prepares you for an important concept, that is decision procedures. You are used to apply decision procedures after you have run an analysis. Right? You will generate a p-value usually, and if that p-value is lower than 0.05, you call it significant. And you claim to have found an effect. And you do so with confidence. But the evidence and the p-value is a continuous measure. Drawing a line in the sand is part of the null hypothesis significance testing framework, but it is not part of the Bayesian framework inherently. You can add a decision procedure, and we will mention those, but we will highly advocate for not using decision procedures. So we are asking you to leave this baggage behind and think more quantitatively. Okay? So that is Bayes' theorem in a nutshell. If you feel a little overwhelmed, that's perfectly fine. There will be several repetitions of core concepts in this class. And the actual formula will not be tremendously relevant for you when you simply apply Bayesian inference to your research question. So don't worry too much. Thank you so much.